Everybody, this is Divya Agarwal. I'm sorry I lost my voice, but today we'll be doing Lab 6, Magnetic Molasses. Introduction. The purpose was to collect observational data of a magnet falling through a conductive tube of foil. We were then going to model the magnet-tube interaction computationally and compare computational predictions with observed data. A brief overview of our results was that we found our experimental time for the magnet to fall to be 1.254 seconds and the computational time calculated to be 0.861 seconds. How do we find out the principles that help us understand this lab? First, we start with Faraday's law, which states that a changing magnetic field through a loop induces a voltage proportional to the rate of change in magnetic flux. The induced voltage opposes the change in flux. This is important because this is how the magnet kind of slows down while falling through the aluminum foil. This also relates to the Biot-Savart law, and both of these act because a steady current produces a magnetic field around it, with the strength depending on the current and distance from the current carrying segment. So depending on the relation of this, the magnetic will fall slower, faster, it'll move differently. And lastly, obviously with all forces, interaction between these two forces, we have Newton's second and third laws, meaning that the net external force equals a change in momentum of a system over time. So basically they're saying that the net momentum is preserved, and this is because the magnet is falling, but different forces are acting on it at different times. And the Faraday's law and Biot-Savart law kind of interact as for every action force, there's equal and opposite reaction force. So for the change in magnetic flux, there's an increase in voltage, and this leads to more of an upwards force acting against the magnet falling down because of the changing magnetic field. And because of these equal and opposite reaction forces, the magnet ends up falling slower. So we'll now go into the procedure and the data. So unfortunately, I was not in attendance, so I do not have an image, but I decided to create a diagram to show you guys what it kind of looked like. I mean, the colors are not accurate, but basically there was a larger loop of aluminum foil, and in that loop we dropped a longer tube magnet down, and it would be sort of levitating, not levitating, but it would be flowing down slower than if you just dropped it on a table. So here's the data. The tube dimensions, the length was 0.455 meters, width being the width, and all these numbers, not exactly too important, right? And the magnet properties we found, the mass was 0.025 kilograms, and the mu of the magnet was 4.613 meters squared. So we have these numbers, and they're important for our computational model. And the average time we found to be t is equal to 1.254 seconds. Sorry. Now we'll go to the computational model. So we're just inputting those base numbers, those base values in the first part, kind of calculating, giving the software something to use. And then when we create the magnet, we're importing some more stuff, the mass, the mu, and sort of visualizing it. And then we calculate the magnetic field using the function and all that stuff. And you can read it if you really are interested, but basically through this we understand the net force because we calculate the gravitational force and the magnetic force as it travels through the loop. And this is what it looks like, the output of the code. So as you can see, like the velocity is the acceleration is changing, right? And it stops when it gets into the tube because that's when the gravitational force is acting on it. So we have only the magnetic force at the start, the gravitational force, and the magnetic force at the oh my gosh. It starts at rest, it goes slower, and it sort of stays at this equilibrium because the magnetic force and the gravitational force are sort of acting equal and opposite, keeping this steady. And there's the visual model of what the magnet looks like at the bottom of the tube, the blue thing. Some assumptions we made in this experiment. We assumed that there was negligible air resistance, and obviously in the real world this is not the case. The magnet has to fall through air, and this would create some aerodynamics issues. We also assume that the bar magnet acts as a magnetic dipole, and this is a bad assumption because it was actually a tube magnet and it may not exhibit these properties. So just thinking about that for the future. And we assumed, again, this is more just a basic assumption we can make with all these labs, that the only forces were the present ones, so the only forces in this being magnetic and gravitational. So here are some what-if questions with the answers. So what if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? So because of the Ohm's law and V is equal to IR, if the resistivity of the conductor were reduced, that means that the current would increase. So that means that the magnet would be slowed because due to Biot-Savart and Faraday's law, it acts proportionally to that. Last question. What if holes or slots were cut into the tube? How would this affect the ring currents in my model? So, because the way that the tube works, there's individual rings of current in the system. So, what would happen if holes and slots were cut into the tube, and this would sort of eliminate some of those current rings as there would be holes, right? So, there would be a weaker magnetic field because there was less current rings, and the magnet would fall faster. Thank you. Again, I apologize. I hope you're able to hear me, but yeah, this is the last lab, so see you guys.